Today we'll be looking at the dot product of algebraic vectors. So to begin, when we were looking in 7.3, so our lesson previously, we dealt with the dot product of geometric vectors, so those vectors that do not have a coordinate system associated with them. So today we're going to look at algebraic vectors, where vectors are involving coordinates in either R2 or R3. So just looking at our computations of the dot product of algebraic vectors in R2 and R3, when looking in R2 here, the dot product between two vectors that exists still is your magnitude of x times your magnitude of y multiplied by cos theta. However, you can also solve this by multiplying x1 by y1 and adding x2 times y2, where x1 and x2 are coordinates of our vector x, and our y1 and y2 are coordinates of your y vector. Similarly, in R3, the only thing different here is that we have a z position, okay, because we're looking at a 3D model here. So in both cases, theta is the angle between our vectors x and y. So if you want to look on page 379 of your textbook, there is a proof for the dot product in R3 using algebraic vectors, as well there's also a proof for the distribution property on page 380. So I'll allow you guys to do that on your own. So with the understanding from our lesson yesterday, we know that the dot product between two vectors x and y is just the magnitude of those vectors multiplied together times by cos theta. However, we can also use that when solving for an angle measurement. So if we have two vectors, as we have here, of a and b, and they're three-dimensional, to find cos theta, this is just equal to the dot product between our two vectors a and b over the magnitudes of our two vectors multiplied, where theta here is the angle between the two vectors. Okay, so that's that angle measurement there. So let's look at an example here. And so given that the vectors a, which is equal to -1, 2, 4, and b, which is equal to 3, 4, 3, we want to calculate the dot product between these two vectors. So as we discussed above, to find the dot product here, we're actually just going to multiply our a1 times our b1, add our a2 times our b2, and add our a3 times our b3. So from there we can multiply those together. So -1 times 3 plus 2 times 4 plus 4 times 3. So that's -3 plus 8 plus 12, and we get that the dot product between our two vectors here is 17. Now, part B in our first example here, we want to calculate to the nearest degree the angle between our vectors a and b, and also we want to include a sketch here. So from our formula for the angle between two vectors, as we just discussed, we can find cos theta by having the dot product of our two vectors over the magnitude of our two vectors. So we already know what the dot product is, as we solved in part A, which is 17. However, we don't know the magnitude. So remember, we're going to find the magnitude, which is just equal to the square root of each of our coordinates squared, and we add them together. So that's -1 squared plus 2 squared plus 4 squared when we're talking about our vector A, which when we do our exponents and add them together, we're going to get the square root of 21, where the magnitude of b, same thing as we did for the magnitude of a, 3 squared plus 4 squared plus 3 squared is going to equal the square root of 34. So that's what our denominator is going to be, the square root of 21 times the square root of 34. And when we calculate that, we're going to get 0.6362. So cos theta is equal to that. Remember, to solve for theta there, we're going to do the inverse of cos theta of 0.6362, and we're going to get that theta is equal to 51 degrees. Okay, it turns out to be about 50.5, so we're going to round that to 51 degrees. Now we also need to draw our sketch. So we can draw our axes here, so remember this is three-dimensional. Okay, so our x, y, and z axes. Now I'm going to go ahead and do my vector A. So vector A, -1, so we go back 1, +2, so right 2 on our y-axis, and up 4. So we're going to have our vector A here. And then similarly for vector B, we're going to +3 on our x-axis, +4, so we're moving right on our y-axis, and up 3. So we'll have something about there. Okay, and that's our vector B, and this angle between there is our theta. So now we can continue looking at our next example here. For what values of m are the vectors x, which is equal to m, -3, and our vector y, which is equal to m, -3, and 6 perpendicular. So when we have perpendicular vectors, we know our theta is equal to 90 degrees, but we also know that the dot product between these two vectors is going to be equal to 0. A very important concept to understand, because we know we can find the dot product between two algebraic vectors by multiplying our x1 by y1, adding our x2 times y2, and then adding our x3 times y3. And since we know when it's perpendicular, our dot product is equal to 0, we can say 0 is equal to, and now our x1 is m times our y1, which is m as well, plus x2 is m, y2 is -3, plus -3 times 6. So then we have 0 is equal to m squared minus 3m minus 18. Now how can we solve from here? We're trying to find what m could be, so we need to factor. So two terms that multiply to -18 add to -3 are -6 and +3. So therefore we have m is equal to 6 and m is equal to -3. So we have two different possibilities here. Now in example 3 we have a parallelogram which has its sides determined by our vector A, which is 6, 1, and our vector B, which is -1, 3. And we want to determine the angle between the diagonals of the parallelogram formed by these vectors. Now I have drawn here my axes are x and y. And what you can note here is that this is in R2, and in this we will first draw out our vectors here. So in our vector A, 6, 1, so we're just going to actually plot 6, 1, so over 6, up 1. Okay. And our vector B, -1, 3, which is B. We know we're talking about a parallelogram, so we also have B over here, and we have A over here. So then we also want to look at our diagonals here. So our diagonals, the pink one, okay, is our A plus B. And then we can also look at our A minus B by looking at the opposite way here. So I'm going to draw that one in green. Okay, so that's A minus B. So when looking at this here, we know that OA, okay, so remember OA just means from your origin to A, okay, is equal to 6, 1, and our OB is equal to negative 1, 3. Now, what we need to do here, since we're trying to find the angle measurement between A and B, so that can either be our theta here, or it could be our beta here. Okay, so it could be two different angle measurements that we're talking about. However, first we need to find, well, what is A plus B? So when we're doing A plus B, we just add our coordinates. So we have 6 plus negative 1 and 1 plus 3, which is equal to 5, 4. And A minus B is equal to 6 minus negative 1 and 1 minus 3, which this will be equal to 7, negative 2. I should have done that one in green, but that's just our A minus B. And then from there, we want to find also our magnitudes, because we know to use our cos theta formula, we need to know both our vectors, okay, and our magnitudes of those vectors. So we can look at A plus B magnitude, which is just equal to the square root of 5 squared plus 4 squared, which gives us the square root of 41. And A minus B, the magnitude of that, is equal to 7 squared plus negative 2 squared, which is equal to the square root of 53. Also, now, cos theta we know is equal to our vectors A plus B, the dot product between these two vectors, and A minus B, all over the magnitudes of those two vectors. And so we know now we can do the dot product here, so of A plus B and A minus B. So we have 5 times 7 plus 4 times negative 2, all over the magnitudes, so the square root of 41 times the square root of 53. When we calculate this, we get 0.5792. Therefore, we get that theta is equal to 54.6 degrees. So we know that theta is equal to 54.6, but what about beta? Beta could be equal to 180 minus our 54.6 degrees, giving us beta being equal to 125.4 degrees. So you have two different options here, which makes sense because we're talking about a straight line. We know all straight lines are 180 degrees. So our last example here is find a vector or vectors perpendicular to each of the vectors, which A is equal to 1, 5, negative 1, and B is equal to negative 3, 1, 2. So when we're talking about perpendicular, this is any given vector x, which is equal to x, y, z. Okay, the dot product of this will be equal to 0. The reason being is because it tells us here that it's perpendicular. So therefore what that means is that the dot product between x and a will be equal to 0, and the dot product between x and b would be equal to 0. So therefore, if we look at the dot product between x and a, this is actually just going to be equal to x plus 5y minus z. And then similarly, if we look at the dot product between x and b, this is going to be equal to negative 3x plus y plus z. So now we have our two equations here by setting these equal to 0. And then we're going to use some elimination here. So we have 0 is equal to x plus 5y minus z, and 0 is equal to negative 3x plus y plus 2z. So we have equations 1 and 2. And what we're going to do here is we're going to multiply 1 by 3. So we have 0 is equal to 3x plus 15y minus 3z. And our second equation, 0 is equal to negative 3x plus y plus 2z. So you can see here that by multiplying our first equation by 3, we're going to be able to eliminate our x's. So we're going to add our 1 and 2 together. So when we do that, we're going to have 0 is equal to 16y minus z. So therefore z is equal to 16y. So what we're going to do, we're going to get everything in terms of y. Because if everything's in terms of one variable, then we can say that our y is equal to another variable such as t, which is what we're going to use, and be able to solve for what our vector could look like. So we have z is equal to 16y. So what we're going to do, we're going to sub z equals 16y into our first equation above here. Okay, so in this equation here. So we have 0 is equal to x plus 5y minus 16y. And what we're going to get is that 11y is equal to x. So we have that our vector x is equal to 11y, y, and 16y. However, we're going to if let t equals y, our vector x will be equal to 11t, t, 16t for any value of t. So you can sub in 2 here, you can sub in half here. Any of those vectors are going to give you perpendicular vectors to both a and b.